All right, today we're going to talk about two different things. We talked about proton chemical shifts, and today I want to talk briefly about C13 NMR shifts. We'll talk more about them later on, but then we're going to start, and we're going to spend a reasonable amount of time talking about spin-spin coupling. And in order to understand this, we really have to understand the concept of chemical equivalence, which ties into concepts of symmetry and stereochemistry and conformational analysis, and it's really beautiful. Chemical equivalence, and so we'll be talking about chemical equivalence and spin-spin coupling. We're actually going to be spending a good deal of time because there's a lot to understand, and as you can already see from the problems, people are saying, hey, what's going on here? And these problems, these very simple molecules, have all sorts of cool issues of spin-spin coupling and all sorts of cool issues of stereochemistry. So we're actually going to spend a number of lectures on them. Next time, we're going to develop a concept called magnetic equivalence, which is different, which is an amplification on chemical equivalence, but it's too much to take in one. And then we're going to spend a couple of times talking about details of spin-spin coupling. All right, what do I want to say about carbon NMR spectroscopy, first of all? All right, if proton NMR was difficult because you have a very small population between your alpha and beta states, carbon NMR is even worse. And first, you know that carbon-12 doesn't have an NMR spectrum. It's not active. It doesn't have a magnetic dipole. And we only have 1%, or more specifically 1.1% C13. So most of your molecules for small molecules don't contain any C13. For small molecules, some of them contain one C13. Now, things get worse. The magnetogyric ratio for C13 is only a quarter that of the magnetogyric ratio for a proton. Now, remember what the implications are of that. That means that you get roughly a quarter, I'll use tildes to say approximately a quarter of the Boltzmann difference, say difference in Boltzmann distribution in alpha and beta states. So already we've got fewer nuclei that can flip up. To put it another way, a 500 megahertz spectrometer gives you a carbon spectrum at 127.5 megahertz, a hair over a quarter, because the magnetogyric ratio is a hair over a quarter. Things get worse than that. Your dipole is only a quarter as strong Guess what? If you want to generate an electric current, like a generator, you want a big hunking magnet to spin in a coil. Proton is a little magnet, but a carbon is a tiny magnet because it's got a quarter of the magnetic dipole. So you're damned again. And then you further get damned because the precession rate is also a quarter. Since for a proton at that same 117,500 Gauss magnet, you're precessing at 500 times per second. For a carbon, you're only precessing at 125 million times, did I say 1,000 million times per second? So that also gives you a quarter as much electricity in the coil. So you've got 1.1% and a quarter of a quarter of a quarter, which means you're only 5,800th as sensitive. Question?
Is that precession rate, are you talking about the Larmor frequency?
The Larmor frequency, yeah. So if you take a magnet and just spin it in a coil, if you spin it faster, you get more voltage. If you spin it twice as fast, you get twice as much voltage. If you take a magnet that's twice as big, you get twice as much voltage. And so for all of these reasons, and you've got, in addition to a smaller magnet, you've got fewer of them because you've got, even if you give a 90-degree pulse, you get only a quarter the magnetic dipole from having only a quarter as many nuclei going down into the XY plane.
Is that a quarter of all? Is that a quarter of what's of protons?
It's compared to protons. So carbon is a much less sensitive technique than proton NMR spectroscopy. Now, there are a few redeeming features. So one thing that's redeeming is we typically do proton decoupling. So normally, a carbon would be split by all of the protons. So for example, the carbon in ethanol would be split into a quartet, in the carbon in the methyl group of ethanol, would be split into a quartet by the 3 hydrogens that are attached to it, and then it would be further split by the hydrogens over on the methylene carbon. But what we do is we irradiate the protons, so all the carbon you're going to see, virtually all the carbon you'll see, is called proton decoupled carbon. That flips the spins of the protons rapidly, which means the carbon doesn't see them as spin up or spin down, so your carbons appear as a singlet. Well, that's good, because that means all your carbon signal is gathered in one peak, so that gives you more intensity. Now, the other thing is when you do that, so that leads to singlets, which is good, sharper, bigger. And the other thing it leads to is what's called the nuclear Overhauser effect. And we'll talk more about this as a technique, but the basic principle of the nuclear Overhauser effect is by perturbing the alpha and beta states of the protons, you end up enhancing the difference in Boltzmann population between the alpha and beta states of the carbon. So that too gives you a bigger signal. So all of this leads to a better signal than you would otherwise get in a proton non-decoupled carbon. All right, anyway, suffice it to say, nowadays it's easy to collect a carbon NMR spectrum. It typically will take more sample. So you can collect the proton NMR sample on strychnine and use a milligram of material or even tenths of a milligram. For a carbon, you might want to put 30 megs in the NMR tube if you have a chance. You know, you can do it at 10. You could do it at a milligram, but it takes a lot more time. And remember, if you have 1 milligram versus 10 milligrams, it's going to take 100 times as long to collect the same signal-to-noise ratio, which means if you're in your research lab and you have some sample, it actually makes sense if you're trying to collect a carbon spectrum to weigh your sample or at least be cognizant of how much you put in your NMR tube, because you want to get your spectrum quickly and you want to get good signal-to-noise ratio. It also makes sense when you're filling your NMR tube to only fill it with the appropriate amount for the coil. The coil on our Brookers is 3.5 centimeters, or requires a 3.5 centimeter high sample. That's a 1/2 mil. So if you dissolve your sample, don't dissolve it in 1.5 mils. Don't try to be clever and dissolve it in 0.3 mils, because then you mess up the shims on the spectrum because you get flux lines at the end of the sample. So anyway, that's the way to get a good spectrum. All right. I want to talk about where the peaks show up. So carbon NMR spectrum, the carbon NMR spectrum has a big range, typically from about 0 to about 200 or 200 and change parts per million, 220, 240 parts per million. Aliphatics show up at about 10 to 40. So on that big range of 200 or so ppm, that's in the upfield region. Carbons next to an electron withdrawing atom show up downfield, but it's not quite as pronounced. So a carbon next to a halogen, you might even sort of see it in this range. Carbon next to a nitrogen, it's going to be sort of at the end of that range. But by the time you're next to an oxygen as an electron withdrawing group, I'd say 50 to 70 for a carbon next to one oxygen. So that sort of stands out. Alkynes aren't that common, but remember I said there's about 2.5 parts per million, 2.2 parts per million maybe for a typical alkyne CH. For an alkyne carbon, it's about 70 to 80 ppm, so that kind of stands out. All right, alkenes and aromatics. Whereas in proton NMR, the alkenes show up a little more upfield, 5 to 6, and the aromatics a little more downfield, 7 to 8. Alkenes and aromatics are all sort of lumped in at about 110 to 150. Beyond about, and of course these are all typical values. If you put in oxygen on an aromatic, like anisole or phenol, where you put an oxygen directly on a carbon, that carbon might be at 160 parts per million. If you have a very electron donor, we'll talk more about specific shifts, but you could easily have, if you have high electron donation, say an orthocarbon, you could easily be a little below 110 ppm. All right, carbonyls, esters, and carboxylic acids, you get a little bit of a resonance effect, so they show up a little bit less far downfield than some of the others. Let's say about 170 to 180 parts per million. Aldehydes show up a little further downfield. Let's say about 190 to 200 ppm. And ketones, I'll say RCOR prime for ketones, let's say about 205 to about 220 ppm. Bless you. I just want to give you one little handout. By the way, if you ever miss your handouts or misplace them, I put them up on the web with the video part of the course, so you can always go ahead and download the handouts. All right, so just as I had my, does anyone else need one? Just as I had my little pigeon drawing of my take of what to look at in reading a proton NMR spectrum, I have my little pigeon drawing of what to take what to look at when reading a C13 NMR spectrum. In other words, this type of region is aliphatics. Here you have a carbon next to a significantly withdrawing group like an oxygen. Here's your alkene aromatics. Here's your esters and acids. Then you go to aldehydes and ketones. So to a large extent, it's sort of like H1 NMR, but with maybe a factor of 20 on the scale. In other words, most of what you're going to see in a proton NMR is from 0 to 10. Most of what you're going to see in a carbon NMR is from 0 to 200. Carboxylic acids will be further out. Ketones will be further out. But that kind of gives you my read on things. All right, this should give you the basics to start to use carbon NMR in helping to analyze some of the homework sets that we're going to get. So one thing that you can get is a reading of things like carbonyl groups in there. And another thing you'll be able to do is count up and see how many different types of atoms, because whereas in proton NMR you may have overlapping resonances, most often because the carbon spectrum is more dispersed and peaks typically show up as singlets, most often you will be able to see one peak for each type of carbon. All right, I want to talk now about spin-spin coupling. We're splitting. And if I had to give you a very, very general way of thinking about it, the way I'll describe it, and we're going to amplify on this in today's talk, the way that I would describe it is that protons, that peaks are split by adjacent protons that are different. And we'll later on amplify on the concept of adjacent, talking about 2-bond coupling, 3-bond coupling, and long-range coupling. But today what I'd like to amplify on is the concept of same and specifically different. So let's start with an example that's very, very, very intuitive. Very, very freshman, sophomore rather. Chemistry, let's take the H1 NMR spectrum of chloroethane. And so my little pigeon sketch of the spectrum of chloroethane would look something like this. We have a 1 to 3 to 3 to 1 triplet, somewhere downfield of 3 ppm, or just a hair downfield of 3 ppm. And then we have a, 1 to 3 to 3 to 1 quartet. And then somewhere just a hair downfield of 1, we have a 1 to 2 to 1 triplet. The triplet comes, of course, from the CH3. And I can say that in this particular example, CH3s are split by the adjacent CH2s. And I can say because the 3 hydrogens of, well, let's talk about the CH2s. The CH2s are split by the CH3. The 3 protons of the CH3 group are the same. So the CH3 does not split each other. So I'll say the CH3 protons do not split each other. And then I'll say in this particular case, the CH2s do not split each other. In other words, in this particular case, the 2 hydrogens of the methylene group are the same, so they don't split each other. But more in general, I'll give this as an exception. So if your compound has a chiral center in it, or the protons are otherwise diastereotopic, then they will split each other. And so this except is something that we're going to be playing with in today's lecture. All right, before we come to this very important concept of diastereotypicity. Let's tackle this basic notion of the 1 to 2 to 1 triplet and the 1 to 3 to 3 to 1 quartet. So we have a triplet, and it's 1 to 2 to 1. It comes from the CH3, and it sees the CH2. And the two protons act as little magnets in each molecule. And those little magnets can be spin up, or one can be spin up and one can be spin down, or they both can be spin down. So you get 3 lines. There's one way for them both to be spin up. There are 2 ways for them to be one spin up and one spin down. And there's one way for them to be spin down. And so that gives rise to our 1 to 2 to 1 triplet. For our quartet, we have a 1 to 3 to 3 to 1 ratio. The quartet, of course, comes from the CH2. The CH2 sees the CH3. And all of the protons can be spin up. In some of the molecules there are. Or 2 can be spin up, and 1 can be spin down, and there are 3 different ways that that can occur. Or 2 can be spin down, and 1 can be spin up. And again, there are 3 ways that can occur. Or they all can be spin down. And we can generalize this idea to say if there are n equal, and I'm going to underline equal, couplings lead to n plus 1 lines. So if there are 4 equal couplings, you get 5 lines. Those 5 lines, it follows Pascal's triangle. You can work out the statistics yourself, or you can say that those 5 lines end up being in a 1 to 4 to 6 to 4 to 1 ratio, and so forth. You basically add the ones above, or you work out the statistics. So for example, if we go to isopropyl chloride, now the CH here is split equally by 3 methyl groups. So the CH appears as a septet, and the ratio of the lines are 1 to 6 to 15 to 20 to 15 to 6 to 1. And because the septet is going to be very small compared to triplets and quartets in the molecule, unless you look hard, you might not see these lines on the outside. And in fact, by the time you get up to very big multiplets like septets and so forth, octets, often people will just report them as a multiplet in reporting an NMR spectrum. All right, let's take a look at a case of what I mean by couplings that may or may not be equal. So imagine the methine group in valine, and specifically this methine group. So this methine group is split by 2 methyl groups. And it's also split by this methine group. And so depending on whether the couplings are equal, that is, whether the coupling constants are equal, it may be an octet. Or it may be more complicated. And I can tell you from experience, in this case, it would be more complicated. It would be, in this case, a doublet of septets, which you would probably report as a multiplet. The OH of alcohols, and I know this has already come up on the homework. The OH of the alcohol may or may not couple. So the hydrogen of isopropanol, the methine of isopropanol, might appear as a septet, or it might be more complicated. In order to couple, this hydrogen has to stick around in one place. It has to stay attached to that proton for a time that's roughly 1 over the coupling constant. In other words, it has to stay attached, since coupling constants are typically on the order of about 7 Hertz. It has to stay attached for hundreds of milliseconds or longer. If that hydrogen exchanges on the order of tens of milliseconds, this methine is not going to see it as either spin up or spin down. It will see an average, and you won't get coupling. If this hydrogen doesn't exchange, then we'll be in the situation here, and it will see it either as spin up or as spin down, and you will have splitting either as an octet or as a doublet of septets, or septet of doublets, depending on the relative J's, but we'll get into that later. Typically, primary alcohols often exchange rapidly. So an alkyne, like an alcohol at the end of a CH2 chain, like you may have in the homework problem, usually will exchange rapidly. Secondary alcohols sometimes do, sometimes don't. They're more sterically hindered. The rate of exchange is going to depend on a number of factors, including the concentration of the sample, because the molecules can exchange by colliding. It will depend on the amount of water in the sample. There's invariably adventitious water in your NMR tube at about 20 millimolar concentration, 10, 20, 30 millimolar concentration. And chloroform undergoes photooxidation to give hydrochloric acid, or DCl in the case of CDCl3. And that will rapidly promote exchange. So if I want to minimize exchange, I typically will pass my chloroform through alumina, not my sample, but my chloroform, through alumina that I've dried over a flame. That'll take out the acid and minimize the amount of water in there. Okay, so alcohols are kind of a wild card on J coupling.
So if the proton is exchanging, do you still see that proton shift?
Do you still see the proton? In general, if the proton is exchanging with other molecules, you will see it, and it will be there. If the proton is exchanging with water, and you have a little bit of water in the sample, you will see it and the water peak at the weighted average of the two. If it is exchanging with water and there's a lot of water, then it will become part of the water peak. Also, there are 2 different time scales. One is the time scale for coupling. The other is the time scale for being able to see a peak. Remember I talked about the uncertainty principle before? So in order to see coupling, your line width has to be, your exchange rate has to be, you have to be able to make the observation such that your line width is on the order of better than 7 Hertz. in order to not have swapping with water, which is very far away, so water is typically 1.6 parts per million in chloroform. Remember I said an alcohol can be 1 to 5 parts per million. Let's take 4 ppm. Those are hundreds or even thousands of hertz away, right? A 4 ppm difference is 2,000 hertz. So in order to not have exchange with water where you can see the alcohol peak, it has to stay attached for tens of milliseconds rather than hundreds of milliseconds. Carboxylic acids are real bad boys in this regard because they do exchange rapidly, which is one of the reasons the peak typically broadens out in chloroform. Alcohols often will stay attached. Secondary amines are a big pain in the ass. Secondary amines are almost impossible to see. You have base catalyzed exchange mechanisms. Primary amines tend to be a little bit better behaved. Aromatic amines are well behaved, so I'm talking aliphatic amines. But if you're working on an alkaloid project or some other project and you have a secondary amine, you really are in trouble.
So you said earlier, like the hydrogen on the carbon adjacent to the alcohol may or may not couple. If that does not couple, can you also assume that the proton on the alcohol will not couple as well?
You mean, yes, it's
like if one doesn't couple, the other one will.
Absolutely. Coupling is mutual.
Okay.
Now, you could envision a circumstance where you had J coupling but quadrupolar broadening. So you could have a hydrogen on a nitrogen that could be broadened to a point where it was a broad singlet, but the hydrogen on the carbon could be split by it, and there the broadening would be quadrupolar. But yes, typically, so again, let's talk in rules rather than exceptions now. Typically, it's going to be seen both ways. Sometimes what will happen is you may, for example, if you have a very complex coupling pattern, if you do have coupling, you may just see this guy as a complex multiplet and then see this guy as a doublet. Why? Because this guy is splitting this guy, but it's such complex splitting that you can't actually discern what the splitting pattern is. On the other hand, it's the same coupling constant, but you only have one coupling and you split into a doublet. Other questions? These are good. These are really important. This is really understanding the real stuff you're going to see in the trenches.
What about the methyl groups?
The methyl groups won't couple to this, will not, because it's far away. In general, coupling is going to be through 2 or 3 bonds, although on the case of double bonds and triple bonds, you can get 4-bond couplings. There's a very good appendix in the back of your book. I forget whether it's Appendix A or Appendix F at the back of Silverstein. What was the appendix? Somebody looked it up. Anyway, that is a very good place to start. But in general, unless you have long-range coupling, we'll get to that in a lecture or two. F. Unless you have long-range coupling, in general, coupling is going to be through 2 or 3 bonds. All right, let us now tackle the concept of chemical equivalence. Chemical equivalence is the first level of sameness that I was talking about. Remember I said that protons only couple to other protons if they are different? 2 protons are the same, are chemically equivalent if they exchange by a symmetry operation, can be exchanged by a symmetry operation or a rapid process. For example, rapid rotation about a bond. All right. The other caveat, and this ties into something I said last time, virtually all, you could say all rotations about sp3 carbon bonds are rapid at room temperature. I'll say virtually always rapid at room temperature. That's a hint. If you see two hydrogens splitting each other and they're both on sp3 carbons attached to each other, chances are you need to think deeper. And it's not, oh, there's some slow process. All right. One corollary to this is chemically equivalent protons have the same chemical shift. So this thing here is kind of like the golden rule of splitting, you know, the basic do unto others as you want others to do unto you. If you keep this in mind, you're going to be very, very well set on all of the details. All right, let's talk about a specific way of thinking about what's the same and what's different. One way that I like to do it, you can do it by couple of ways. If you're good with symmetry, you can just go ahead and say, all right, do we have a symmetry operation that interchanges these two hydrogens, say in diphenyl methane? You can say they interchange by reflection, and therefore they are chemically equivalent. But we're going to get into some cases that at least the first time you see them are tricky. And another way to do it is just to perform a little thought experiment and say, all right, what is their topological relationship to each other? And the way you do this thought experiment is you replace one proton by a deuterium and the other proton by a deuterium. And then you ask yourself, what is the relationship between these two molecules? And in the case of this particular thought experiment, these two are the same. And since they're the same, topologically, we call those two protons homotopic. And homotopic protons are chemically equivalent. Let's try another molecule. Obviously, these are trivial. So let's take, instead of diphenylmethane, let's take ethylbenzene. And again, we'll consider the methylene group. The two hydrogen groups of the methylene group still exchange by reflection. So they meet the criterion there. They're chemically equivalent. Yeah? You can't tell them apart, so they have the same chemical shift. And two protons that are chemically equivalent are the same and don't split each other. So chemically equivalent protons don't split each other. Now, later on, we're going to talk about a concept called magnetic equivalence. And what you'll see is that although chemically equivalent protons, well, actually, I'm going to hold off on this statement here. Right now, I'm just going to leave it as there are two types of sameness, and chemically equivalent protons don't split each other if they are also magnetically equivalent. But we're going to get to that later. For now, the simple rule is chemically equivalent protons are the same in a certain way. All right, let's try our little Gedonk experiment here. We replace one by a deuterium, and we replace the other by a deuterium. And now, these two molecules, are they the same? No. What are they? Enantiomers. So now they are enantiomers, which means topologically the protons are enantiotopic. And enantiotopic protons are also chemically equivalent. All right. So now let's come to a molecule where we have a chiral center in the molecule. And since we've been building on this idea of phenyl groups, I'm going to give us the molecule phenylalanine. Doesn't matter whether I draw it racemic, which means we have two enantiomers, or whether I have one molecule. OK. These two protons are now no longer exchangeable by reflection. And no matter how rapidly you rotate, they still are not the same. So these two protons now, the methylene protons, are not chemically equivalent. And let's try our thought experiment here again, because sometimes things can get more complicated than you might anticipate. And so we'll take one, replace it with a deuterium, and we'll take the other and replace it by a deuterium. And we'll ask ourselves what the relationship of those two structures is to each other. What are they? They're diastereomers. So we say that the two hydrogens of the methylene group are diastereotopic. And therefore, they are not chemically equivalent. All right. So here's a spectrum of phenylalanine so we can see what's going on. This is a spectrum taken in D2O with DCl to dissolve it, deutero-HCl to dissolve it. So all of the OHs and the NHs have exchanged with deuterium and are exchanging rapidly, and for all intents and purposes don't J-couple. So we see a peak for our HOD, and then we see the rest of it are carbons attached to hydrogen. We see our phenyl group over here in the 7 to 8 range. We see our proton connected to the alpha carbon over here, just a hair down field at about 4.3 parts per million. And then we see our beta protons, the ones that are next to the phenyl, and we see them as 2 peaks. Each of the beta protons appears at and these are expansions here. Each of the beta protons appears at distinct positions. They're not the same. They're not chemically equivalent. They could be coincident, meaning appearing at the same position, but they are not. And so they appear at different positions. And what's more, each of them is a doublet of doublets, or DD. Why? Because each of the protons splits the other one and is split by the alpha. So we have both a J2 HH, that's a 2-bond coupling, since you go 1-2 bond to get from these 2 beta protons to each other. And we have a 3-bond coupling between the alpha proton and each of the beta protons. And the alpha proton is also a doublet of doublets. So each proton is a doublet of doublets. The alpha proton is a doublet of doublets because it's split by the 2 beta protons, and it's split with different coupling constants. The beta protons are coupling to the alpha proton probably with about 6 and 8 Hertz coupling constants, and we'll be talking more about these in a moment or in a future lecture. And the beta protons are coupling to each other with about a 13 or 14 Hertz coupling constant. All right. Let's talk about why we have to keep our heads attached to us. So I'm going to give us another example. And the example I'll give us is a molecule called acetal. Acetal is acetaldehyde diethyl acetal. All right, so what do we have here? We have a couple of ethyl groups, and we have a methyl group. The CH3s of the ethyl group appear here as a triplet. So this is OCH2, CH3. That looks pretty reasonable. We have another methyl group. It appears as a doublet That's our CH, CH3. That looks pretty reasonable. We have our methine. It's the one that's attached to 2 oxygens. So it's shifted downfield. It's at 4.6 parts per million. It's a quartet because it's split by the methyl group. And finally, we come to the CH2s. And the CH2s show up as 2 peaks. And it takes a moment to wrap your head around this. And to wrap your head around this, what you have to realize is that these 2 protons are not chemically equivalent. You can think of this a couple of ways. They don't exchange by a symmetry operation. If you reflect through the plane, you don't get the same thing. Another way to think about it, and I think the easiest way to keep your head on straight, is to think about it rigorously. You imagine replacing one of them with a deuterium, replacing the other of them with a deuterium, and the molecules that you get are diastereomers. In other words, these 2 protons are diastereotopic.
We talked about in IR how if you have like an internal alkene, sometimes you don't see the stretching because there's like that pseudo-symmetry. Do you see the same thing with this, that if you have like a stereoisomer or like a stereocenter, but it's like really far away?
Absolutely. Great question. Just because 2 protons are topologically diastereotopic doesn't mean that they won't be coincident. And in general, the further that they are from the stereocenter, the more likely they are to be coincident and behave as if they are equivalent. Here we see them as well-defined peaks at very different positions. They're both doublets of quartets. That's a DQ, whoops, DQ. And we'll talk more about the splitting pattern, but they're being split with one big geminal coupling of about 10 hertz, 1 2-bond coupling, and with 3 vicinal couplings, 3 3-bond couplings of about 7 hertz. All right, last thing I want to show you. One last handout while we're on the concept of chemical equivalence. So here we have the molecule 3-methyl-2-butanol. And what I want to point out to you is in 3-methyl-2-butanol, the 2 methyls are not the same. They're diastereotopic. You can think of this a couple of ways. One way is to think about, remember the OH constitutes a chiral center, and you can do a little thought experiment and say, all right, I'll envision replacing one of the methyl groups or the other methyl group with a deuteromethyl group. Or the other way is just to think about the topology. But when you look at it, you say, all right, how many peaks do we see in the C13 NMR? 1, 2, 3, 4, 5. There are 5 types of carbon because there are 5 non-chemically equivalent carbons. If you look at the proton NMR, it's a little confusing at first until you think about what's going on. It's not hard to realize that this methyl group that's beta to an oxygen gives rise to this doublet. Now we have 2 more methyl groups in the molecule. And each of those methyl groups is next to a hydrogen. Each of those methyl groups appears as a doublet, but the doublets are very close. In other words, we have a doublet, and we have another doublet, and so it looks like a triplet.
Can you discern that because it's not the 1 to 3 to 1?
What's that?
Can you discern that because?
Well, you can discern it if you look carefully, because it's not 1 to 3, 1 to 2 to 1, but it's confusing. So it's 2 doublets, but let me tell you a secret. This is a 300 megahertz spectrum. Remember I said the coupling constant is fixed in hertz. The position is fixed in ppm. So my 2 doublets would look like this at 300, and it would look like a triplet. If I went to 500 megahertz, the 2 doublets would now separate, and I'd see a doublet and a doublet, and that would be one way you could prove it. All right, I think that's what I want to say for today about chemical equivalence. We'll pick up next time talking about magnetic equivalence.